This is the formula for gravity. I'm just going to pull it out of the hat here. Okay. The force of gravity between two objects. Okay. And this is, and I don't know if you guys recognize this, okay, but 9.8 meters per second squared is not a universal constant. It doesn't even work very well up at Timberline Lodge. Certainly, on the top of Everest, it's definitely off by significant amounts. And by the time you get to the moon, it's just a memory, right? So the 9.8 is not a fundamental constant, okay? But this is our first fundamental constant. We believe anywhere in the galaxy you go, okay, this G that's in this formula is always going to be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, okay? So put that in on your cheat sheet. There it is. You need to know that, right? So this is universally the force of gravity between any two objects that have mass in the universe. This is universal gravitation, okay? Now, to be careful and do careful work, notice that if the objects are spheres, if they're points, it's no problem. Just measure the distance between the 2 points, right? And plug it in. Okay? If they are spheres, it's still no problem. You just measure the center to center distance, right? So the distance between us and the Earth is not 0, it's the radius of the Earth. Standing on the surface of the Earth, our distance center to center is, according to gravity, the radius of the Earth, okay? And then it doesn't matter which order you put the masses in because multiplication is communistic, right? It doesn't matter. Isn't that the communist property of math? A times B equals B times A. What is it really? What's it called? Is that commutative? Yeah, there we go, right? Okay. So, and then this is our constant. The way that you figure out the G, by the way, is that you actually measure the force of gravity between two objects whose mass you know. Now, that's weird. You probably don't think there's a force of gravity between this mass and this cutie. Is that a cutie? Party in your tummy. Yeah, there we go. Right? Okay, that's what it says on there. I didn't make that up, right? Okay, I bet you think there's not a force of gravity between this and this. But there is. In the same way that there's a force of gravity between you and the Earth, there's a force of gravity between these two things. In fact, kids were like, no, that's not true. Well, if you stick these things, if you take two 1 kilogram masses, place them 1 meter apart, one here, the other one here, okay? And leave them, if you put them in deep space, far away from any other gravitational influence, they will drift together. And they'll do it in a matter of days. They'll drift toward each other and eventually just be like you guys at a dance. Just right up against each other. No, I'm just kidding. You guys don't dance that way, do you? No. Base to base, you leave lots of space, right? Okay. So anyway, so that's right. That's right. You leave room for the deity of your choice, right? Okay. So the first thing I want to do is I want to measure the force of gravity between a stapler and a marker. And by the way, this marker is like made of like osmium or something. It's like 0.341 kilogram marker, right? But let's just go with it, right? Okay. So let's figure out the force of gravity. It's going to be really, really small, but let's see how small it is. And let's also practice using our calculators. Okay. So take your calculator out. Here's our formula: is F is G m1 m2 over r squared. Okay. And so we're going to plug in our numbers: 6.67 times 10 to the minus 11th, and this is Newton meters squared per kilogram squared. I'm only going to put the units in like this once to show you how they cancel. The first mass is 0.756 kilograms. The second mass is 0.341 kilograms, right? So these are just two ordinary objects. They are 1.75 meters away. That's an ordinary distance. And don't forget to square your 1.75. Now, when you put it in your calculator, poles make it look like this: 6.67. Do not go times 10 raised to the, don't do that, okay? Okay? Yeah, what you want to do is go second EE, right? 6.67 second EE has to be the unary minus, minus 11, right? And now we're good. Times 0.756 times 0.341 divided by 1.75 squared. Yeah? So it's a second function on your TI-83 calculators. Something that really gives me, I really don't like that. It's like, what was more important than scientific notation that you do all the time when you're typing in numbers? X to the minus 1? I don't think so. Right? But anyway, yeah? What do you get? Do you get like a really, really small force? Yeah, this is like an incredibly small force, like 5.6. Has everybody done this? I would like everybody to do this, to get a calculator out, type this in. Yeah.
So what's the S equals G and then we don't use that one?
We did. That's what we just used, right? That's the formula. Right. There you go. This is universal. It's a different constant. Yeah, you don't have to write it on your whiteboard. We'll do some that we'll whiteboard, but we won't whiteboard these. These are just examples. Has everybody figured out how to where their E button is? It says EE. You only get one E out of it, though, yeah? Has everybody done that? Here, I need you to do it. I need you to get a calculator. Yeah? I don't know. I don't know why they say EE, right? What? Second, you'll see it. Connor, Hines. If I walk back there, am I going to see this on your calculator? What? I need you to type this in your calculator. Is that a free program? Yeah. Technically not. You're supposed to get, what it is an emulator. The programming of a TI calculator is proprietary, right? But what you can do is take the image, you can actually take the ROM image from the calculator and pop it into it, right? And then it's good. But I just found somebody who posted the image on the internet and just popped it in there because I didn't know how to get the ROM image from it. I can set you up with it if you want. You know. I want a touch screen so I can be like the math teachers, right? Yeah. They've got the fancy TI thing. This one's free. I kind of like that, right? Okay. Are we all good? Has everybody successfully used scientific notation and gotten this number? Yeah, there we go. So point being with this thing, that's an exceedingly small force. If that force acted without opposition for a period of a couple days, it actually would probably bring those things together because there's nothing else going on. It'd be like, it's so bored. It's like, what do you, well, I'm going to accelerate. Nothing else to do, right? You know? So let's do something a little more exciting. Let's figure out, okay, let's figure out the force of gravity on a 1 kilogram mass that's on the Earth. So it is the radius of the Earth from the center of the Earth, right? It's the radius of the Earth from the center of the Earth. Oh, before we do that, let's just look at the units, okay? Do you see that kilograms and kilograms cancel kilograms squared, meters squared cancels meters squared? We're left with what units? Newtons, right? That's the units are just made up so that we get newtons, okay? So now let's do the surface of the Earth. Here's the Earth. All right, here's a kilogram mass, a really big kilogram mass, right? I mean, if the kilogram mass were that large, why? Anyway, okay. So this distance here is 6.38 times 10 to the 6th meters. That's the radius of the Earth, right? The mass of the Earth is 5.97 times 10 to the 24th kilograms, right? Okay, and this mass here is 1.0 times, well, just 1 kilogram, right? Okay, so now we're set. Let's type the numbers in to our calculators, right? So it's going to be 6.67 E minus 11, right, times 5.97 E 24.